Okay, we have been working with quadratic function graphs so far, and I would like to extend this to cubic functions and quartic functions and so on and so on. So let's try an example. Y equals to, say, x minus 1, x plus 1, x minus 2. What will be the graph of that? Well, now, I would like to view this function in two different ways. This is in factor form, but we can also multiply them out, right? You can FOIL it. So I can multiply these two together. X times x is x squared. X times 1 is plus x. Negative 1 times x is minus x. Negative 1 times 1 is minus 1. And then these two cancel, and you have x squared minus 1 times x minus 2. X squared times x is x cubed. X squared times negative 2 is negative 2x squared. Negative 1 times x is negative x, and negative 1 times negative 2 is positive 2. Okay, so what kind of graph is this? It's a cubic graph. What's the end behavior? Right, yeah, that's the end behavior. Yeah, somebody in the audience was doing this. That's very good. Yeah, that's very good. Yes, yeah, that's exactly right. Okay, so I know that the graph must be doing something, but in between something's happening. What's happening here? That's what we need to know, right? Okay. So back to our original function, and you didn't really have to do all that computation to see that the end behavior is that. All you had to do was just look at the highest order terms. It's x, x, x. If you multiply that, what do you get? X cubed, positive x cubed, right? So from there, you can immediately say that the end behavior should be this. Okay? Oh, why did I do that? When I do this, when I turn around, like all the graphs become like flipped. So. Sorry about that. That's the correct end behavior, right? Okay. So now the next thing I want to do is to find the intercepts, because often intercepts help us to identify what's happening, right? So what is the x-intercept? X-intercept. That's when y is equal to 0, right? So we set y as 0. You have x minus 1, x plus 1, x minus 2. Solve this. Well, if something's multiplied to give you 0, at least one of them has to be 0. Either x minus 1 is 0, which means x should be 1, or x plus 1 is 0, which means x should be negative 1, or x minus 2 should be 0, which means x is equal to 2. So you know that when x is 1 or negative 1 or 2, at those places y becomes 0, so these are the x-intercepts. Good? Makes sense, right? Okay, what about the y-intercept? How do you get the y-intercept? Set x equal to 0. So y is 0 minus 1, 0 plus 1, 0 minus 2. Let's see, negative 1 times 1 is negative 1, negative 1 times negative 2 is positive 2. Okay. So here is what we figured out so far. We know that 1, 2. This is your y-intercept. We also know that x-intercept is at negative 1. Oh, I think it's closer. Something here. Negative 1. And also at 1. And also at 2. We also know that the end behavior is something like this. So what do you think the graph would be? It should be passing through like that? Yeah. Right. So that's the graph of x cubed.
What's the thing for that?
You can't do it. You just have to do motions like that. Yeah.
Like this.
Yeah. Yeah. Yeah, but doing that makes it fun, and it makes it easier to understand what's going on.
Can I do that during
Now, yeah, you can do it during. Oh no, but then other people are going to see your work, and then they can cheat off of you. So that's
How am I
not
supposed
good.
to do it?
Well, you use your imagination,
Yeah,
all right?
you get it.
Okay. Now,
Gio?
there's one thing that I have to say, however. See, if you use some online graphing website and plug this in, you're going to see this graph, and you can verify that you're right. But here's some additional things that you should know to make sure that you got it right. So, see, a quadratic equation had how many vertex? There was a single vertex for a quadratic function, right? Now, for a cubic function like this, you don't call these points as vertex. We just call them as turning points. Or another way to call that is you call this relative maximum because it's higher than the nearby ones. Okay. This one is also called a turning point, but in this case, you also call this point a relative minimum because it's lower than the nearby points. Okay, so there's relative minimum, relative maximum, and these are all called turning points. Okay, how many turning points do you see? Two. Now, it's a cubic function. Do you think that has the number of turning points have anything to do with the cubic function?
Yep.
Yeah.
3 turning points.
No, cubic function will have 2 turning points. Okay. Quadratic function will have 1. So if you have order 4 polynomial, how many turning points would it have? 3. So it's 1 less than the order. However, it's not always the case. It's like that's the maximum number of turning points. So in fact, so we'll just say that our solution is done. I'm now trying to explain the general theory of this. In fact, here's what happens. If you have a quadratic function with this being positive, if a is positive, then a general, did I say quadratic? Sorry, I mean cubic. If you have a cubic function with a being positive, then the general shape of a cubic is something like this. Here, here, or this. Okay? Now this is the case when in the middle it's like flat. Okay? So if you modify the b and c and d, well, d only makes it go up and down, so it doesn't matter. But if you modify b and c a little bit, then you can change the location of those turning points, and at some point the turning points will become closer and closer together, and when they just meet, what happens is that they become flat like this, and that's when poof, the turning points go away. You don't have any turning points in this case, right? And then if you go further, then it just gradually increases. There is no turning point. It always increases. Okay? If you have a turning point, what does that mean? That means it goes from increasing to decreasing, right? Yeah. So increase here, and then decrease there, and then increase. So such a behavior would be seen if you had a turning point, but see here, it always increases. It always increases. For these two cases, there is no turning point at all. Okay, and that also happens in quartic. Let me try to explain the quartic. The general shape of a quartic looks like. So if you had a quartic, that means 4th power 3 to x plus e. In that case, you have, if a is positive, then here's the generic form. It's like, yeah. So that's, you have how many turning points in this case? 1, 2, 3. 3 turning points, right? Now, depending on how you change the value of b and c and d, these locations of the turning points can merge and disappear and so on and so. So there are a lot more possibilities here. And what happens is, like, one example is like you could have something like that. That will be the case where this stays as it is, but these two kind of merged and it became this. Okay? Now, another thing that you can see in a quartic case is because the graph's end behavior is like that, right? It will always have some minimum, right? So there will be at least one turning point. Okay? So a quartic graph will have maximum of how many turning points? 3. 3 is the maximum. Minimum, 1. This will be the case when you have 1, right? And so on, so on. If you have a, to summarize, maybe I should write it, okay? So, f of x equals to ax to the n plus bx to the n minus 1 c. This is called degree n polynomial. And sometimes instead of degree n, people call this as the order of the polynomial. So order of the polynomial has at most how many turning points?
3.
No, n degree polynomial. How many turning points is the maximum?
N minus 1.
N minus 1. That's the important thing I wanted to show.